Hello, linear maps, kernel of f, mf, image of a basis of an injective map, rank theorem, things you heard about, but have you ever really understood them? And have you ever imagined what they look like? Yes, you heard me well. How they look like. In this video, we will visualize these concepts and their secrets so you can have a better concrete understanding of them. We start with linear maps, their definition and 1D examples. If you work in the context of R vector spaces, a linear map is by definition a map defined from an R vector space E into an R vector space F. The space E is called the domain, the space F is called the codomain, and it should satisfy the following. For all x in E, for all y in E, f of the sum x plus y is equal to the sum of the images, so f of x plus f of y. Then, for any x in E and for all alpha in R, f of alpha x is equal to alpha f of x. If we take the particular case when E is equal to f is equal to R, so the one-dimensional case, then the linear maps will only be written as f of x equals a times x, where a belongs to R. These are the only linear maps that can be written from R into R. In a first example, we take the map f of x equals 3x. What does this map in practice do? It takes a number and multiplies it by 3. So, if we visualize the axis of the real numbers, calculating the images of all the real numbers will be like multiplying all of them by 3. The image of the segment 0, 1, for instance, will be the segment 0, 3. So the linear map f of x equals 3x applied to the real axis will be like applying a zoom of factor 3 for this axis. In a similar way, the map f of x equals half x applied to the real axis will be like contracting by a factor of half this axis. In a similar way also, the linear map f of x equals minus 2x applied to the real axis will be like inverting the direction and magnifying the axis by a factor of 2. Let's recall now the definition of the kernel and the image of f to apply them in this example. The kernel of f is defined as the space or the elements of the domain whose images are the null elements. So they are the elements of E such that f of x is equal to the null element, the 0 of f. The set mf is the set of all elements of f having pre-images. So mf is equal to all the elements of f y such that there exists x in E verifying f of x equals y. Then, in the considered examples, the only element in Ker f, the kernel of f, is the number 0. So the kernel of f is only equal to the set containing one element 0. But since for any element in the codomain R, so any real number practically, we can't find a pre-image, take for instance the case of the first example, f of x equals 3x. Then for any number y in the codomain, 1 over 3 of y will be an element of the domain R, which is a pre-image of y. Therefore, any element in the codomain R has a pre-image. That's why mf is equal to R in all three examples. Let's now consider the case of linear maps in 2D. So we consider now linear maps from R2 into R2. So from a two-dimensional space into a two-dimensional space as well. Take first the case of a map that will multiply, let's say, the components of any element of the domain R2 by 3. So it will be written as f of x, y equals 3x, 3y. As you know, any linear map between finite dimensional spaces can be represented by a matrix. So for this example, the matrix can be written as 3, 0, 0, 3. we can easily see this by multiplying the matrix 3, 0, 0, 3 by any vector xy, which will give us 3x, 3y, which is the image of xy by f. So what's the visual effect of this linear map on the domain R2? Multiplying both components by 3 will be like magnifying the space R2 by a factor of 3. It's an expansion by a factor of 3, as we can see on the graph representing this transformation. Above you can see the space R2, and below you can see the transformed space after it has been expanded by a factor of 3. Let's try now the visual effect of other linear maps, then of course other matrices. So take for instance the matrix 2, 0, 0, 1. What will be the effect? This matrix or this linear map will expand only the first component by a factor of 2. What about this one, 2, 0, 0, 4? It will expand the first component by a factor of 2 and the second component by a factor of 4. But what will be the effect of a non-diagonal matrix? The matrix 2, 0, 4, 3, for instance, will expand the first component by a factor of 2. And the second component, it will be rotated and then expanded by a factor of square root 4 squared plus 3 squared, which is 5. The matrix 2, 5, 4, 3 will expand and rotate both components. Now, what will happen if we have negative values? The matrix minus 3, 0, 0, 1 will invert the direction and expand only the first component by a factor of 3, while the matrix minus 3, 0, 0, minus 2 will invert both directions and expand them as well, and so on. Minus 2, 0, minus 4, 3, minus 2, minus 5, 4, 3, minus 1, 2, minus 3, 2. In all the considered examples, you can easily see graphically that for any element in the domain R2, there exists a unique image in the codomain R2. And for any element in the codomain R2, there exists a unique pre-image in the domain R2. The linear map would be then bijective. In all these cases, it's also very intuitive graphically to see that the only element whose image is 0, 0 is the element 0, 0 itself. Then the kernel of f contains only the element 0 of R2. Also, mf is equal to R2. Then the dimension of kernel of f is 0 and the dimension of mf is 2, which confirms the rank theorem that says that the sum of the dimensions of kerf and mf is equal to the dimension of R2, which is in this case 2. You might also notice that in all the examples we considered, the two columns of the matrix were linearly independent, so its rank was always 2. So what will happen if it's not the case? Let's take, for example, a linear map whose matrix is 2, 0, 0, 0 of rank 1. So we have two columns that are dependent. So this matrix will expand the first component by a factor of 2, but it will make vanish the second component, as you can see on the figure. So the two-dimensional space will collapse into one axis. Therefore, mf is reduced to an axis, a one-dimensional space, while the one dimension somehow lost by mf is gained by kerf, whose dimension goes to 1, since the elements, and only these elements, whose images are 0 of R2, are the elements of first component null. For instance, if you take the matrix 2, 0, 0, 0 times 0, 5, that's equal to 0, 0. This shows the behavior of the rank theorem, which ensures the mutuality between the dimensions of mf and kerf. In this case, the map is no longer injective. Many elements can have the same image, 0 of R2. This is a representation of the equivalence between the injectivity and the fact that the kernel of f should be equal to 0 of R2. It's not surjective neither, since any element with a non-zero second component has no pre-image. Let's check now other matrices with linear dependent columns. 1, 2, 2, 4, 3, 3 half, 2, 1, 2, 4, minus 3, minus 6, minus 1, minus 3, 2, 6, 2, 4, 2, 4, and 4, 2, 6, 3. We always have the same behavior where the two components are multiplied by a factor and rotated. The linear map transforms them the two-dimensional space and collapses it into a one-dimensional space. Finally, what about the determinants? Let's go back to the case of the map represented by the matrix 2, 0, 0, 3. The determinant of this matrix is 6. Geometrically speaking, it represents the ratio of the area of a transformed figure by the area of the original one. Take the unit square of area 1, let's say. The transformed shape is a square of area 6. Then the determinant will be 6 over 1, which is 6. This holds up for any map. In any other example, it will always be the case. Calculate always the ratio of the transformed unit square with respect to the unit square, and you'll find the determinant. When the determinant is negative, it means that only one of the directions is inverted. When it's positive, it means either no inversion of the directions or both are inverted. When the determinant is 0, it means that the space R2 is collapsed into one axis, so the area of the transformed shape is 0, which is equivalent to the fact that the columns are dependent. Thank you for watching, and hope these concepts are no longer an abstract theory for you.